Hello there. Tonight we're drifting toward our closest celestial companion, the moon. For thousands of years, humans have gazed upward at that glowing orb, weaving stories and seeking answers in its gentle light. But the moon holds far more secrets than our ancestors could have imagined. Tonight, we'll explore the fascinating truths hidden in its ancient surface, its mysterious origins, and the quiet ways it shapes our world every single day. Some of what we'll discover will feel familiar, like the way moonlight has guided travelers through countless nights. Others will surprise you, like how the moon is slowly stealing time from our days, or how its surface holds clues to the violent birth of our solar system. Each revelation will draw you deeper into the story of this silent guardian that has watched over Earth for billions of years. As we journey together through these lunar mysteries, you might find your thoughts becoming softer, your breathing slower, and your mind ready to drift into peaceful sleep. That's perfectly natural. Let these facts about the moon wash over you like gentle waves on a quiet shore. If you enjoy these nighttime explorations into the wonders of space, feel free to like and subscribe and share your thoughts in the comments below. But for now, all you need to do is get comfortable, let your eyes rest, and allow the ancient wisdom of the moon to carry you gently toward dreams. The moon is moving away from Earth at the speed of a fingernail growing. Every year, our celestial companion drifts approximately 3.5 centimeters farther from us. This gradual retreat is caused by the same tidal forces that pull our oceans back and forth each day. As Earth's rotation slowly transfers energy to the moon, it pushes our satellite into a slightly higher orbit. This process has been happening for billions of years, and it means that long ago, the moon appeared much larger in our sky than it does today. Ancient observers would have seen a moon that loomed dramatically overhead, creating total solar eclipses that lasted much longer than the brief moments we experience now. The moon's slow journey away from Earth also affects the length of our days. As the moon recedes, Earth's rotation gradually slows, making each day a tiny fraction longer. In the distant future, perhaps 50 billion years from now, the moon will appear as just a small, distant point of light, and our days will stretch to equal about 47 of our current days. The moon has no atmosphere to speak of, yet it experiences weather of sorts. Without air to cushion incoming objects, meteorites strike the lunar surface with full force, creating the countless craters that scar its face. These impacts happen constantly, though most are too small for us to see from Earth. Occasionally, astronomers detect brief flashes of light on the moon's surface, marking the moment when a space rock meets its end in a violent collision. The lack of atmosphere also means the moon experiences temperature swings that would be impossible on Earth. During the lunar day, which lasts about 2 weeks in Earth time, surface temperatures can soar to over 250 degrees Fahrenheit. But when the sun sets on any given location, temperatures plummet to nearly -400 degrees Fahrenheit. There's no air to hold on to the sun's warmth, so heat radiates directly back into the cold vacuum of space. The moon's surface is covered in a fine, powdery dust called regolith. This isn't ordinary dust like you might find on a bookshelf. Lunar dust is created by billions of years of meteorite impacts grinding rocks into increasingly smaller particles. Because there's no wind or water to smooth these particles, they remain sharp and jagged, almost like microscopic glass shards. Apollo astronauts discovered that this dust clings to everything, getting into equipment, spacesuits, and even the lunar modules they use to return to Earth. The regolith layer varies in thickness across the moon's surface, sometimes reaching depths of several meters. Beneath this dusty blanket lies solid rock, much of it formed during the moon's violent early history when massive impacts melted and reformed the surface repeatedly. The dust itself holds a record of cosmic history containing particles not just from the moon itself, but from the solar wind and even distant stars that have blown across space for eons. The moon's far side looks dramatically different from the face we see each night. While the near side features large, dark plains called maria, formed by ancient volcanic activity, the far sideus. This stark difference puzzled scientists as heavily cratered and mountain for decades after the first photographs were taken by Soviet spacecraft in the late 1950s. We now understand that the near side's thinner crust allowed molten rock to flow more easily to the surface, creating the smoother plains, while the far side's thicker crust preserved more of the early bombardment craters. The far side also experiences a very different relationship with Earth. From there, our planet never rises or sets in the sky. Instead, Earth hangs motionless in the lunar heavens, slowly cycling through its phases as it rotates. An observer on the far side would see Earth as a brilliant blue marble, showing different continents and weather patterns as our world turns, but never moving from its fixed position among the stars. The moon influences Earth's tides in ways that go far beyond simply raising and lowering sea levels. The gravitational pull that creates our ocean tides also affects the solid Earth itself, causing the ground beneath our feet to rise and fall by several inches each day. This solid Earth tide is usually imperceptible to us, but sensitive instruments can measure it easily. Even the atmosphere experiences tidal effects, with air pressure fluctuating slightly in response to the moon's position. The moon's tidal influence extends to many aspects of life on Earth. Some marine creatures time their reproductive cycles to the lunar calendar, releasing eggs and sperm into the water during specific moon phases, when tides create the most favorable conditions. Certain coral species spawn en masse during particular lunar cycles, creating underwater snowstorms of new life. Even some land animals seem to respond to lunar rhythms, though the mechanisms behind these connections remain partly mysterious. The moon rotates on its axis at exactly the same rate that it orbits Earth, which is why we always see the same side facing us. This phenomenon, called synchronous rotation or tidal locking, developed over millions of years as Earth's gravity gradually slowed the moon's rotation until it matched its orbital period. This isn't a coincidence unique to our moon. Many moons throughout the solar system are tidally locked to their parent planets, suggesting it's a natural outcome of gravitational forces over long periods of time. Before tidal locking occurred, an observer on Earth would have seen the moon slowly rotating, revealing different hemispheres over the course of its orbit. The process of achieving synchronous rotation involved the gradual transfer of rotational energy from the moon to its orbital motion, which also contributed to the moon slowly spiraling outward from Earth. This same process is still happening today, though so slowly that the changes are barely perceptible over human timescales. The moon's gravity is only about 1/6 as strong as Earth's gravity. This weaker gravitational field has profound implications for anything on the lunar surface. A person who weighs 180 pounds on Earth would weigh only 30 pounds on the moon, though their mass would remain the same. This reduced gravity allowed Apollo astronauts to leap and bound across the surface in ways that would be impossible on Earth, despite wearing heavy spacesuits and life support equipment. The weaker gravity also means the moon cannot hold onto an atmosphere the way Earth can. Any gas molecules that might be released from the lunar surface, perhaps by impacts or outgassing from rocks, quickly escape into space. This is why the moon remains airless despite billions of years, during which various processes might have released gases from its interior. Water exists on the moon, but not where you might expect to find it. While the sunlit lunar surface is bone dry, scientists have discovered significant deposits of water ice in permanently shadowed craters near the moon's poles. These regions haven't seen sunlight for billions of years, creating natural freezers where water delivered by comets and asteroids has accumulated over geological time. Some of these ice deposits may contain millions of tons of water, enough to support future lunar missions and even permanent lunar settlements. The discovery of lunar water ice has changed how we think about the moon's potential for supporting human exploration. Water can be split into hydrogen and oxygen, providing both rocket fuel and breathable air for astronauts. It can also be used for drinking, growing food, and shielding against radiation. These polar ice deposits represent one of the moon's most valuable resources for future space exploration. The moon played a crucial role in stabilizing Earth's axial tilt over geological time. Without our large satellite's gravitational influence, Earth's rotational axis would wander much more dramatically, causing extreme climate variations that might have prevented complex life from developing. Mars, which lacks a large moon, experiences chaotic changes in its axial tilt over millions of years, leading to dramatic climate swings. Earth's moon acts like a cosmic gyroscope, keeping our planet's seasons relatively stable and predictable. This stabilizing influence extends to Earth's day length as well. The moon's presence has helped slow Earth's rotation from what may have been a 6-hour day in the early solar system to our current 24-hour cycle. Without the moon's tidal-breaking effect, our planet might still be spinning rapidly, creating extreme weather patterns and making the development of complex life far more challenging. Moonlight is simply reflected sunlight, but it undergoes interesting changes during its journey from the sun to the moon to our eyes. The moon's surface reflects only about 12% of the sunlight that hits it, making it actually quite dark by comparison to many other objects. Fresh snow reflects about 90% of sunlight, making it far more reflective than the lunar surface. The moon appears bright to us only because it's set against the dark background of space, and because our eyes are adapted to perceive even small amounts of light. The quality of moonlight differs from direct sunlight in subtle ways. Lunar light is slightly redder than sunlight because the moon's surface absorbs more blue wavelengths than red ones. This shift is usually too small for our eyes to detect, but sensitive instruments can measure the difference. The moon also polarizes light slightly as it reflects it, a property that some animals may use for navigation during nighttime hours. Human cultures have long recognized patterns in the moon's changing appearance, dividing the lunar cycle into distinct phases that repeat every 29.5 days. This lunar month became one of humanity's first reliable ways of tracking time, predating more complex calendars based on the sun's yearly journey. Many languages still carry echoes of this lunar timekeeping, with words for month often relating to the moon itself. The timing of the lunar phases depends on the moon's position relative to Earth and the sun. When the moon lies between Earth and the sun, we see the new moon phase, where the lunar surface appears dark from our perspective. As the moon moves along its orbit, more of the sunlit side becomes visible, progressing through crescent, quarter, and gibbous phases until the full moon, when Earth lies between the sun and moon and we see the entire illuminated hemisphere. Lunar eclipses occur when Earth's shadow falls across the moon's surface, temporarily dimming or darkening our satellite. Unlike solar eclipses, which can only be seen from specific locations on Earth's surface, lunar eclipses are visible from anywhere on Earth where the moon is above the horizon. During a total lunar eclipse, the moon often takes on a reddish color, earning the nickname blood moon. This red coloration comes from Earth's atmosphere bending red light around our planet's edge, casting a rusty glow on the lunar surface even as it sits in Earth's shadow. The frequency and timing of lunar eclipses follow predictable patterns that ancient astronomers learned to calculate with remarkable accuracy. These cycles repeat roughly every 18 years and 11 days, a period known as the Saros cycle. By understanding these patterns, early civilizations could predict when eclipses would occur, often leading to important cultural and religious observances timed to these celestial events. The moon's surface preserves a record of the early solar system that has been erased from most other worlds. Because the moon lacks an atmosphere, weather, and tectonic activity, impact craters from billions of years ago remain largely unchanged. By studying the size, distribution, and age of these craters, scientists can piece together the history of impacts throughout the inner solar system. The heavily cratered lunar highlands tell the story of the late heavy bombardment, a period roughly 4 billion years ago when asteroids and comets rained down on the inner planets with devastating frequency. This ancient bombardment shaped not only the moon, but also Earth, Mars, and the other terrestrial planets. On Earth, erosion and plate tectonics have erased most traces of this early violence. But the moon serves as a faithful witness to those chaotic times. Each crater tells a story of cosmic collision, preserving evidence of the raw materials and energy that help forge the worlds we see today. Human exploration of the moon remains one of our species' greatest achievements, yet it represents just the beginning of our relationship with our celestial neighbor. The 12 astronauts who walked on the lunar surface between 1969 and 1972 collected samples, conducted experiments, and took photographs that continue to yield new scientific insights decades later. Their footprints remain perfectly preserved in the airless environment, unmarked by wind or weather, silent testimony to humanity's first steps beyond our home planet. The legacy of lunar exploration extends far beyond the scientific knowledge gained during those brief visits. The technological innovations developed for the moon missions led to advances in computers, material science, and engineering that continue to benefit us today. The perspective gained from seeing Earth as a small, fragile sphere suspended in the cosmic dark helped foster a new environmental awareness that continues to influence how we think about our place in the universe. As we continue our gentle journey through these lunar mysteries, let the ancient rhythms of our celestial companion guide your thoughts toward rest. The moon has been Earth's silent guardian for billions of years, and it will continue its patient orbit long after we've all returned to the stardust from which we came. In its steady presence, there's a comfort that transcends the boundaries of time and space, a reminder that some things endure far beyond the brief span of any single life. The moon's formation remains one of the most compelling mysteries in planetary science. The leading theory suggests that early in Earth's history, a Mars-sized object called Theia collided with our young planet in a catastrophic impact that ejected massive amounts of material into orbit. Over time, this debris coalesced to form the moon we see today. This giant impact hypothesis explains many peculiar features of the Earth-Moon system, including why both bodies have similar compositions and why the moon has a relatively small iron core compared to other rocky worlds. The violence of this ancient collision would have been unimaginable. The impact likely vaporized much of both Theia and the early Earth, creating a ring of molten rock and metal around our planet. Within just a few hundred years, this material began clumping together under its own gravity, gradually building the moon from countless smaller pieces. The newly formed moon would have been much closer to Earth than it is today, appearing as a massive, glowing sphere in the sky, its surface still molten from the heat of formation. Evidence for this dramatic origin story comes from analyzing the rocks brought back by Apollo missions. These samples show that lunar material has been thoroughly mixed and melted, consistent with formation from a debris disk. The moon's composition also closely matches Earth's mantle, suggesting the two worlds share a common heritage. Even today, scientists continue to refine their understanding of this cosmic collision, using computer simulations to model how such an impact might have unfolded over hours and days. The moon's interior structure tells a story of gradual cooling and differentiation over hundreds of millions of years. Like Earth, the moon has a layered structure with a small metallic core surrounded by a rocky mantle and crust. However, the proportions are quite different from our planet. The lunar core makes up only about 2% of the moon's total mass, compared to Earth's core, which represents roughly 30% of our planet's mass. This difference supports the impact theory, as much of the iron from both colliding bodies would have remained with Earth due to its stronger gravitational field. Seismic instruments left behind by Apollo astronauts revealed that moonquakes occur regularly, though they're much weaker than earthquakes and have different causes. Some moonquakes happen when the moon's interior adjusts to tidal stresses from Earth's gravity. Others occur when the lunar surface contracts as it cools in Earth's shadow during eclipses. These seismic waves travel through the moon differently than they would through Earth, confirming that our satellite has its own unique internal structure. The moon's magnetic field, or rather its lack of one, provides clues about its thermal evolution. Today, the moon generates no global magnetic field because its small core has cooled and solidified. However, rocks from the lunar surface contain traces of ancient magnetism, suggesting that the moon did possess a magnetic field billions of years ago when its core was still molten and convecting. This ancient magnetic field would have helped protect the early lunar atmosphere from being stripped away by the solar wind, though it wasn't strong enough to prevent the moon's eventual transition to its current airless state. Studying the moon's gravitational field has revealed hidden structures beneath its surface. Spacecraft orbiting the moon have detected gravitational anomalies called mascons, short for mass concentrations, which represent areas where denser material lies buried under the lunar crust. Many of these mascons correspond to the large impact basins that formed when asteroid-sized objects struck the moon billions of years ago. The impacts fractured the crust and allowed dense mantle material to well up from below, creating permanent gravitational signatures that persist to this day. The moon's influence on Earth extends beyond tides to affect our planet's very structure. the gravitational dance between Earth and Moon causes both worlds to wobble slightly as they orbit their common center of mass, called the barycenter. This point lies about 1,700 kilometers below Earth's surface, roughly a quarter of the way from our planet's center to its surface. As the Earth-Moon system orbits the Sun, this barycentric motion creates subtle variations in our planet's path through space. These gravitational effects have practical consequences for space navigation. Mission planners must account for the Moon's position when calculating trajectories for interplanetary spacecraft. The Moon's gravity can be used to accelerate or redirect spacecraft, a technique called a gravitational slingshot. Several missions to the outer solar system have used lunar flybys to gain speed and adjust their paths, turning the Moon into a stepping stone for exploring the cosmos. The lunar regolith contains a detailed record of solar activity spanning billions of years. As the solar wind, a stream of charged particles from the Sun, strikes the airless lunar surface, it becomes embedded in the fine dust and rock fragments. By analyzing these solar wind particles trapped in lunar samples, scientists can study how the Sun's output has changed over geological time. This information helps us understand not only solar evolution, but also how variations in solar activity might have affected Earth's climate throughout history. Helium-3, a rare isotope deposited on the lunar surface by the solar wind, has captured the imagination of those planning future energy systems. This isotope could theoretically power clean fusion reactors that produce no radioactive waste. While fusion technology using helium-3 remains decades away from practical application, the Moon's surface contains vastly more of this material than exists naturally on Earth. Some visionaries imagine future lunar mining operations that could harvest helium-3 to power Earth's energy needs, though the technical and economic challenges remain formidable. The Moon's phases have guided human activities for millennia, but they also affect the behavior of countless other species. Many marine organisms synchronize their reproductive cycles with lunar phases, taking advantage of the extreme tides that occur during new and full moons. Sea turtles often nest during specific lunar phases, and some fish species time their spawning to coincide with tidal cycles. Even terrestrial animals show lunar rhythms, though the mechanisms behind these connections often remain mysterious. Research into lunar biological effects continues to yield surprising results. Some studies suggest that human sleep patterns may be subtly influenced by the lunar cycle, with people sleeping less soundly around the full moon. While the evidence remains debated, it's possible that evolutionary remnants of ancient rhythms still echo in our biology, connecting us to the same celestial clockwork that guides marine creatures and shapes the tides. The Moon serves as Earth's first line of defense against cosmic impacts. Its gravitational influence helps sweep potentially hazardous asteroids and comets out of Earth-crossing orbits, reducing the frequency of major impacts on our planet. Without the Moon's protective presence, Earth would likely suffer more frequent bombardments from space debris. The lunar surface itself bears witness to this protective role, covered with craters that represent impacts that might otherwise have struck Earth. This cosmic shielding effect works over long time scales, gradually perturbing the orbits of objects that might threaten Earth. While the Moon cannot deflect everything, its gravitational influence creates a more stable environment in Earth's neighborhood, contributing to the conditions that have allowed complex life to evolve and thrive on our planet. temperature variations across the lunar surface create a complex thermal environment that changes dramatically with the sun's position. Areas near the lunar equator experience the most extreme temperature swings, baking in direct sunlight for 2 weeks before plunging into frigid darkness for another 2 weeks. Near the poles, some crater rims remain in perpetual sunlight, while the crater floors lie in permanent shadow. These permanently shadowed regions serve as natural cold traps, preserving ice and other volatile materials for billions of years. The thermal properties of lunar regolith create interesting effects during temperature transitions. The dust acts as an insulator, so while the surface temperature changes rapidly when sunlight arrives or departs, temperatures just a few feet below the surface remain relatively stable. This thermal layering could be important for future lunar habitats, which might be built underground to take advantage of the more moderate subsurface temperatures. Lunar dust poses unique challenges that extend far beyond its sharp, clingy nature. The lack of atmosphere means there's no weathering process to round off the microscopic, glass-like particles created by eons of meteorite impacts. This dust carries an electrostatic charge from interactions with the solar wind, causing it to levitate slightly above the surface and stick to virtually everything it touches. Apollo astronauts discovered that lunar dust could penetrate seals, clog mechanisms, and even cause spacesuits to overheat by coating their cooling radiators. Understanding and managing lunar dust will be crucial for future long-term missions to the moon. Engineers are developing new technologies to minimize dust problems, including specialized coatings, electrostatic cleaning systems, and habitat designs that can better seal out the abrasive particles. The challenge of lunar dust represents one of the most practical obstacles to establishing permanent human presence on our celestial neighbor. The moon's synchronous rotation means that radio communications with Earth are impossible from most of the far side. This radio shadow creates both challenges and opportunities for lunar exploration. While it complicates communications with far-side missions, it also provides a uniquely quiet radio environment, shielded from Earth's electromagnetic noise. This makes the far side an ideal location for radio telescopes that could detect faint signals from the early universe, free from the interference that plagues Earth-based observations. Future lunar observatories could take advantage of this radio silence to peer deeper into space and time than ever before. The moon's lack of atmosphere and geological stability make it an excellent platform for all kinds of telescopes, from radio arrays that could span hundreds of kilometers to optical instruments that never have to contend with atmospheric distortion. As our exploration of lunar mysteries continues, each fact reveals new layers of connection between our world and its ancient companion. The moon's story is intertwined with Earth's history in ways both obvious and subtle, from the dramatic impact that may have formed it to the gentle gravitational embrace that continues to shape our planet's evolution. In understanding the moon, we better understand ourselves and our place in the vast cosmic dance that began billions of years ago and continues still, one quiet orbit at a time. The moon's gravity creates invisible rivers in space that spacecraft can follow like cosmic highways. These gravitational pathways, called Lagrange points, exist where the gravitational forces of Earth and Moon balance in perfect equilibrium. Objects placed at these points can remain relatively stationary with minimal energy expenditure, making them ideal locations for space telescopes, communication satellites, and future space stations. The James Webb Space Telescope currently occupies one of these gravitational oases, positioned beyond the Moon's orbit where it can observe the universe without interference from Earth's heat signature. These cosmic balance points shift and flow as the Moon orbits Earth, creating dynamic corridors that mission planners can exploit to send spacecraft across vast distances using surprisingly little fuel. Some missions have taken meandering paths through multiple Lagrange points, essentially surfing on gravitational waves to reach their destinations. This celestial choreography represents a kind of space-age navigation that would have seemed like magic to earlier generations of astronomers. The Moon's surface contains mysteries written in languages we're only beginning to decipher. Strange swirls of magnetized rock spiral across certain regions, creating patterns visible even from Earth through powerful telescopes. These magnetic anomalies may represent the fossilized remains of ancient magnetic fields, or they could mark where solar wind particles have been deflected by local magnetic fields over millions of years. Some of these swirls appear to correlate with regions that reflect more sunlight, suggesting complex interactions between magnetism, solar radiation, and the lunar surface. Recent observations have revealed that some of these magnetic swirls change over time, shifting and evolving in ways that scientists don't fully understand. The Moon may be more dynamic than its ancient cratered appearance suggests, with subtle processes continuing to reshape its surface in ways that unfold over decades rather than geological ages. Moonbeams carry information about the vacuum of space itself. As sunlight reflects off the lunar surface and travels to Earth, it passes through the near-perfect vacuum between the two worlds. This journey, while seeming empty, actually takes place through a medium filled with charged particles from the solar wind, magnetic fields, and quantum fluctuations that modern physics suggests fill even the emptiest regions of space. Sensitive instruments can detect these subtle influences in reflected moonlight, using our satellite as a cosmic laboratory for studying the properties of vacuum itself. The space between Earth and Moon also serves as a testing ground for understanding how light behaves over astronomical distances. Some theories predict that light might change slightly during very long journeys through space, effects too small to detect over shorter distances but potentially measurable across the 250,000 miles between worlds. Lunar soil possesses properties that make it both a challenge and an opportunity for future exploration. The regolith can be sintered or fused together using focused sunlight or microwave energy, potentially creating construction materials for lunar bases. This process could transform the abrasive dust that plagued Apollo missions into building blocks for permanent structures. The same material that threatens to jam mechanisms and of humanity's first permanent tier spacesuits might someday form the walls and foundations foothold beyond Earth. Experiments have shown that certain types of plants can actually grow in lunar soil, though they struggle compared to Earth-grown counterparts. These findings suggest that with proper treatment and supplementation, lunar regolith might support agriculture in pressurized greenhouses, providing food for future lunar settlers. The chemical composition of moon dust includes many elements essential for plant growth, though in proportions quite different from terrestrial soils. The moon's lack of weather creates a preservation environment unlike anywhere on Earth. Footprints left by Apollo astronauts remain as crisp today as when they were first made over 50 years ago. Equipment left behind by various missions sits exactly where it was placed, unchanged by wind, rain, or corrosion. This makes the moon a kind of museum of space exploration, where every human artifact remains in pristine condition. This preservation extends to natural processes as well. Impact glass formed by ancient meteorite strikes retains its original properties, allowing scientists to study billion-year-old collision events as if they happened yesterday. Volcanic features on the moon appear exactly as they did when they formed, providing windows into lunar geology that would be impossible to study on more active worlds. The moon generates its own faint atmosphere through a process called sputtering. High-energy particles from the solar wind strike the lunar surface and knock individual atoms loose from rocks and soil. These ejected atoms form an incredibly thin atmosphere so tenuous that it's technically called an exosphere. This ghostly atmosphere contains sodium, potassium, and other elements that create a barely detectable glow around the moon's edge, visible only with the most sensitive instruments. During meteor showers, when Earth passes through streams of cosmic debris, the moon experiences its own version of these celestial fireworks. Meteoroids strike the lunar surface and vaporize instantly, adding temporary clouds of atoms to the already thin exosphere. These lunar meteor showers create brief, bright flashes visible from Earth, marking moments when small pieces of asteroids or comets meet their end in silent explosions across the airless lunar plains. The moon's influence on Earth's rotation has consequences that ripple through many aspects of our planet's behavior. As tidal friction gradually slows Earth's spin, the length of our days increases by about 2 milliseconds per century. This might seem insignificant, but over geological time, these tiny changes add up. Fossil evidence from ancient corals suggests that Earth days were only about 22 hours long when complex life was first evolving in the oceans hundreds of millions of years ago. This gradual slowing affects everything from weather patterns to the behavior of ocean currents. As Earth's rotation slows, the Coriolis effect that shapes wind patterns and storm systems gradually weakens. Climate models suggest that this could influence long-term weather trends, though the changes unfold so slowly that they're overwhelmed by other factors operating on human timescales. Deep beneath the moon's surface, radioactive decay continues to generate small amounts of heat, a remnant of the violent processes that formed our satellite billions of years ago. This internal heat source, while much weaker than Earth's geological engines, may keep small pockets of the lunar interior slightly warm. Some scientists speculate that these warm zones might preserve traces of water or other volatile materials that escaped from other parts of the moon long ago. The gradual cooling of the moon's interior causes the entire satellite to shrink very slowly, creating stress fractures called thrust faults across its surface. These lunar wrinkles mark where the moon's crust has buckled and folded as the interior contracts. Some of these faults show signs of recent activity, suggesting that the moon continues to experience small moonquakes as it adjusts to ongoing shrinkage. The moon serves as a gravitational lens that can focus radio waves from distant cosmic sources. This natural focusing effect, similar to how a magnifying glass concentrates light, could potentially be used to study extremely faint radio signals from the early universe or even search for signs of extraterrestrial intelligence. The technique would require precisely positioning radio telescopes to take advantage of the moon's gravitational focusing, but the potential scientific rewards could be extraordinary. This gravitational lensing effect also influences the paths of spacecraft passing near the moon. Mission planners must account for these subtle deflections when calculating trajectories. but they can also use them to fine-tune orbital paths with minimal fuel expenditure. The moon's gravity field serves as both a challenge and a tool for space navigation. Ancient impact basins on the moon tell stories of collisions so violent they nearly shattered our satellite. The largest of these basins, called the South Pole Aitken Basin, stretches across nearly a quarter of the moon's circumference and penetrates deep into the lunar mantle. This massive scar represents one of the largest impact features in the entire solar system, created when an asteroid the size of a small planet struck the moon early in its history. The shock waves from this impact would have traveled completely through the moon and focused on the opposite side, creating the chaotic, mountainated from deep within the moon Wassus terrain that characterizes much of the lunar far side. Material excavated scattered across the surface, providing samples of the lunar interior that would otherwise remain forever buried. Future missions to this ancient impact site could reveal secrets about the moon's formation and early evolution. The moon's phases create subtle but measurable effects on Earth's atmosphere. As the lunar gravitational field varies with the moon's position, it creates atmospheric tides similar to ocean tides but much smaller in magnitude. These atmospheric fluctuations are too small for humans to notice, but they can be detected by sensitive barometric instruments. Some researchers have even suggested that these atmospheric tides might influence weather patterns, though such effects would be extremely subtle compared to solar heating and other major climate drivers. The changing illumination of the moon also affects the amount of reflected sunlight reaching Earth at night. During full moon, the additional light can suppress the formation of certain types of clouds and may influence nocturnal animal behavior on a global scale. These effects represent yet another way that our celestial companion continues to shape conditions on Earth through mechanisms both obvious and hidden. Lunar geology preserves evidence of the sun's past behavior in ways that Earth's dynamic surface cannot. Solar wind particles embedded in lunar rocks provide a record of how our star's output has varied over billions of years. By analyzing these ancient solar particles, scientists can study whether the sun has always shone with steady brightness or if it has experienced periods of unusual activity that might have affected Earth's climate throughout history. This geological record suggests that the young sun was actually dimmer than it is today, a finding that creates puzzles for understanding early Earth's climate. Despite receiving less solar energy, Earth's oceans remained liquid during the period when life was first evolving, suggesting that other factors such as atmospheric composition played crucial roles in keeping our planet warm enough for biology to emerge and flourish. The moon's gravity creates tidal effects in the solid Earth that extend far beyond the surface. Deep within our planet, the lunar gravitational field causes rock to flex and flow in response to changing tidal stresses. These deep timing and the circulation of molten rock in earth tides may influence volcanic activity. Earthquake, they represent another way that the moon continues to shape Earth's mantle. While these effects are small, our planet's internal dynamics over geological time. Some researchers have proposed that tidal stresses from the moon might even influence the timing of major earthquakes, though the evidence remains controversial. The idea suggests that when tidal forces are at their peak, they might provide just enough additional stress to trigger earthquakes that were already close to occurring naturally. As we continue drifting through these lunar revelations, each new understanding deepens our appreciation for the complex relationship between Earth and its celestial partner. The moon emerges not as a simple, dead rock circling our planet, but as an active participant in Earth's ongoing story, influencing everything from the length of our days to the behavior of life in our oceans. Its ancient surface serves as both library and laboratory, preserving records of cosmic history while continuing to teach us about the forces that shape worlds. In the gentle rhythm of the moon's phases and the steady pull of its gravity, we find patterns that have guided life on Earth for billions of years. These same forces that lifted ancient seas and shaped the evolution of countless species continue their patient work today, reminding us that we are part of a cosmic dance that began long before consciousness emerged and will continue long after our brief moment in the sun has passed. The moon watches over this endless waltz with the same serene patience it has shown since the violent birth of the Earth-Moon system, a silent witness to the beauty and complexity that can emerge when worlds find their rhythm together in the vast darkness of space. The moon's interior contains secrets that challenge our understanding of planetary formation. Recent gravitational mapping by orbiting spacecraft has revealed dense regions deep beneath the lunar surface, suggesting that the moon's core may be more complex than previously imagined. These gravitational anomalies hint at the possibility of partially molten regions that persist even today, billions of years after the moon's formation. The discovery suggests that our celestial companion may still harbor pockets of geological activity, hidden beneath its seemingly lifeless exterior. These dense regions appear to be distributed unevenly throughout the lunar interior, creating a kind of three-dimensional puzzle that scientists are still working to solve. Some of these anomalies may represent remnants of the original magma ocean that covered the moon during its violent birth, while others could be the signatures of ancient impact events that drove dense material deep into the lunar crust. Each gravitational measurement adds another piece to this subsurface mystery. The moon experiences its own version of seasons, though they're nothing like the familiar cycles we know on Earth. Because the moon's rotational axis is tilted only slightly compared to Earth's dramatic 23-degree tilt, lunar seasons are subtle and relate more to the changing angle of sunlight hitting different regions over the course of the moon's orbit around Earth. Near the lunar poles, some areas experience periods when the sun barely skims the horizon for days at a time, while others enjoy extended periods of continuous illumination. These polar lighting conditions create unique environments that may preserve different types of materials in different locations. Areas that receive more consistent sunlight tend to have different chemical signatures from those that spend extended periods in shadow, suggesting that even subtle variations in illumination can influence the composition of the lunar surface over long periods of time. Lunar rocks contain isotopic signatures that tell stories of cosmic violence stretching back to the earliest days of the solar system. The ratios of different elements found in moon samples provide clues about the composition of the solar nebula from which all the planets formed. Unlike Earth rocks, which have been recycled through plate tectonics and weathering processes, lunar samples preserve their original chemical fingerprints with remarkable fidelity. These isotopic records suggest that the early solar system was a much more chaotic place than the relatively peaceful neighborhood we see today. The moon's rocks contain evidence of multiple generations of stellar explosions that occurred before our solar system formed. their exotic elements now locked forever in the crystalline structure of lunar minerals. Each sample brought back by the Apollo missions represents a time capsule from this ancient epoch. The lunar surface reflects different colors of light in ways that reveal its mineral composition to observant astronomers. While the moon appears uniformly gray to the naked eye, careful spectroscopic analysis reveals subtle color variations across different regions. The ancient lava flows that created the Maria have different reflective properties from the highland regions. And even within these broad categories, smaller variations hint at different mineral compositions and formation processes. These color differences become more apparent when viewed through filters that isolate specific wavelengths of light. The moon takes on an almost painted appearance when seen this way, with blues indicating areas rich in certain minerals, and reds highlighting regions with different chemical compositions. This hidden rainbow of lunar geology provides a map of the moon's formation history written in reflected starlight. The moon's gravitational field varies in strength across its surface due to variations in the density and thickness of the crust below. These gravitational variations are subtle but measurable, creating invisible hills and valleys in the moon's gravitational landscape. Spacecraft orbiting the moon must constantly adjust their trajectories to account for these variations, which can pull them off course if not properly anticipated. The strongest gravitational anomalies correspond to the large impact basins where dense material from the lunar interior was excavated and redistributed during massive collisions. These gravitational scars persist billions of years after the impacts that created them, serving as permanent reminders of the violent bombardment that shaped the early solar system. Future lunar missions may use these gravitational maps to locate the most scientifically interesting landing sites. Volcanic activity on the moon occurred much more recently than scientists once believed. While most lunar volcanism ended billions of years ago, some volcanic features appear to be only millions of years old, practically yesterday in geological terms. These young volcanic deposits suggest that the moon's interior may have remained partially molten much longer than expected, challenging theories about how quickly small planetary bodies should cool and solidify. The discovery of recent volcanic activity has implications for understanding the moon's thermal evolution and the possibility that some volcanic processes might continue even today. While no active volcanism has been detected, the relatively young age of some volcanic features suggests that the moon's geological story may not be as finished as its cratered surface initially suggests. The moon serves as a natural particle detector, recording the passage of cosmic rays and solar wind particles in the structure of its surface rocks. Over billions of years, high-energy particles from space have gradually altered the crystal structure of lunar minerals, creating microscopic tracks that can be analyzed to understand the history of cosmic radiation in our solar system. These tracks provide information about solar activity, galactic cosmic rays, and even the passage of our solar system through different regions of the galaxy. By studying these particle tracks in rocks of different ages, scientists can reconstruct how the intensity and composition of cosmic radiation has changed over time. This information helps us understand not only the history of our local cosmic environment, but also how cosmic radiation might have affected the development of life on Earth throughout its history. The moon's far-side radio silence has revealed unexpected discoveries about the local space environment. Without Earth's electromagnetic interference, sensitive radio telescopes on lunar missions have detected faint signals that would be impossible to observe from Earth's surface. Some of these signals appear to come from the interaction between the solar wind and the moon's weak magnetic field remnants, while others may represent previously unknown types of cosmic radio emission. These observations from the lunar far side have opened new windows into space, physics, and astronomy. The pristine radio environment allows for studies of the cosmic microwave background radiation, the afterglow of the Big Bang, with unprecedented clarity. Future permanent radio observatories on the far side could revolutionize our understanding of the early universe and the fundamental nature of cosmic phenomena. Lunar dust grains contain microscopic spheres of glass created by the intense heat and pressure of meteorite impacts. These tiny glass beads, called spherules, form when rock is instantly vaporized and then rapidly cooled during impacts. Each spherule represents a moment of cosmic violence frozen in time, preserving conditions that existed for mere milliseconds during impact events billions of years ago. The composition and structure of these glass spherules provide clues about both the impacting objects and the lunar rocks they struck. Some spherules contain rare elements that are more common in asteroids than in lunar rocks, providing direct samples of the cosmic debris that has bombarded the moon throughout its history. Others preserve evidence of the extreme temperatures and pressures generated during large impacts. The moon's gravity creates standing waves in Earth's atmosphere that can influence weather patterns on a regional scale. These atmospheric gravity waves, triggered by the moon's gravitational pull, can affect cloud formation and wind patterns in ways that are only beginning to be understood. While these effects are subtle compared to solar heating and other major climate drivers, they represent another mechanism through which our celestial companion continues to influence Earth's environment. Research into these atmospheric effects has revealed correlations between lunar phases and certain types of weather patterns, though the relationships are complex and often masked by other meteorological factors. The moon's gravitational influence on the atmosphere adds another layer to the intricate web of forces that shape Earth's climate system. Temperature measurements across the lunar surface have revealed unexpected variations that don't follow simple patterns of sunlight and shadow. Some areas remain warmer than expected even in shadow, while others cool more rapidly than theoretical models predict. These temperature anomalies may be caused by variations in the thermal properties of different types of lunar rock, or don't yet understand. The thermal they might indicate subsurface heat sources that we behavior of the lunar surface also provides insights into the physical properties of the regolith layer. Areas covered by thicker dust layers show different thermal responses than regions where solid rock lies closer to the surface. These thermal signatures help scientists map the thickness and composition of lunar soil from orbit, providing valuable information for planning future landing missions. The moon's weak magnetic field remnants interact with the solar wind in ways that create miniature versions of Earth's auroras. These lunar auroras are invisible to the naked eye but can be detected by sensitive instruments that observe ultraviolet light. The interactions occur where ancient magnetic field lines preserved in certain lunar rocks deflect incoming solar wind particles and cause them to emit faint glows. These magnetic interactions also create small-scale phenomena similar to Earth's radiation belts, though much weaker and more localized. Understanding these processes helps scientists better understand how magnetic fields protect planetary atmospheres and what conditions were like when the moon possessed a stronger global magnetic field billions of years ago. Seismic waves from moonquakes travel through the lunar interior differently than earthquake waves travel through Earth, revealing fundamental differences in internal structure. The moon appears to have a partially molten layer that affects how seismic energy propagates, creating a kind of acoustic shadow zone where certain types of waves cannot penetrate. These seismic signatures provide the most direct evidence we have about conditions deep inside our celestial neighbor. The patterns of moonquake activity also reveal ongoing stress within the lunar crust as the moon continues to cool and contract. Some moonquakes occur along fault lines created by this shrinkage, while others appear to be triggered by tidal stresses as Earth's gravity flexes the lunar interior. These seismic events, though much weaker than typical earthquakes, demonstrate that the moon remains a geologically active world. The lunar horizon appears much closer than Earth's horizon due to the moon's smaller size and curvature. An astronaut standing on the lunar surface can see only about 2.5 kilometers to the horizon, compared to nearly 5 kilometers visible from the same height on Earth. This compressed horizon creates a sense of standing on a small world, where the curvature of the surface is readily apparent, even without traveling far from a landing site. This foreshortened perspective affects how lunar explorers navigate and plan traverses across the surface. Landmarks that appear close may actually be much farther away than they seem, while features that look small from a distance may prove to be substantial obstacles when approached. The compressed scale of the lunar landscape creates unique challenges for both human explorers and robotic missions. Lunar eclipses visible from the moon would show Earth as a brilliant ring of fire surrounding a dark silhouette. During these events, an observer on the lunar surface would see all of Earth's sunrises and sunsets simultaneously, as our planet's atmosphere refracts sunlight around its edges. This ring of light would appear much brighter than the dim red glow we see during lunar eclipses on Earth, creating a spectacular celestial display that no human has yet witnessed firsthand. The duration and frequency of these Earth eclipses as seen from the moon follow different patterns than lunar eclipses observed from Earth. Because Earth is much larger than the moon, Earth eclipses would last longer and occur more frequently for a lunar observer. The shadow cast by Earth on the moon creates a moving zone of darkness that travels across the lunar surface, offering future lunar residents the possibility of witnessing some of the most dramatic celestial events in the solar system. The moon's surface contains natural glass formations created by ancient volcanic activity that differ significantly from impact glass. These volcanic glasses formed when lava containing dissolved gases erupted onto the airless lunar surface, creating formations unlike anything found on Earth. Without atmospheric pressure to contain the gases, lunar volcanic eruptions would have created spectacular fire fountains that scattered glass droplets across vast areas. Some of these volcanic glass deposits contain water and other volatile compounds that were trapped during the eruption process. These deposits represent some of the most accessible sources of water and other resources on the lunar surface, potentially more valuable than the ice deposits in polar craters because they're located in areas with better solar exposure and easier access for future missions. Lunar soil mechanics present unique challenges that Earth-based experience cannot fully prepare us for. The combination of low gravity, vacuum conditions, and electrostatically charged dust particles creates a material that behaves unlike any terrestrial soil. Lunar dust can flow like a liquid in some situations while clumping together in others. depending on factors like temperature, electrostatic charge, and the mechanical disturbance it experiences. Understanding these unusual soil properties is crucial for designing equipment and habitats that can function reliably on the lunar surface. Everything from rover wheels to habitat foundations must be engineered to work with soil that has no moisture content, no organic matter, and physical properties that change dramatically with temperature and mechanical disturbance. The moon's synchronous rotation creates permanent day and night sides, but the boundary between these regions experiences a slow, eternal sunset that lasts for days. Along this terminator line, the sun appears to hover just above or below the horizon for extended periods, creating lighting conditions unlike anything experienced on Earth. These regions of perpetual twilight may offer unique advantages for future lunar settlements, providing consistent, low-angle sunlight that could be ideal for solar power generation. The slowly moving terminator also creates temperature gradients that might be exploited for generating power through thermoelectric devices. The contrast between the sun-baked day side and the frigid night side creates a thermal gradient that persists as long as the sun continues to shine, offering a potential source of continuous power that doesn't depend on storing energy through the long lunar night. Ancient lava tubes beneath the lunar surface may provide natural shelters for future human settlements. These underground chambers, formed when flowing lava created hollow tunnels through solid rock, could offer protection from radiation, temperature extremes, and meteorite impacts while providing large enclosed spaces for habitats and equipment. Some of these lava tubes may be enormous by terrestrial standards, potentially large enough to house entire cities within their protected confines. Identifying and exploring these subsurface features represents one of the most exciting possibilities for future lunar exploration. Ground-penetrating radar and gravitational mapping have already identified likely locations for these hidden chambers, and future missions may focus on accessing and characterizing these natural underground spaces that could serve as humanity's first permanent homes beyond Earth. As these lunar mysteries continue to unfold in your mind like chapters in an ancient story, let them guide your thoughts toward the peaceful rhythms of sleep. The moon has kept its patient vigil over Earth for so long that its light has witnessed the rise and fall of countless civilizations, the evolution of life from the simplest organisms to the complex thoughts now drifting through your consciousness. In its steady, predictable cycles, there is something deeply comforting, a reminder that some things endure beyond the brief span of human concerns. The gentle pull of lunar gravity that moves our oceans also moves through your dreams, creating tides of rest that ebb and flow with the same ancient rhythms that have shaped life on Earth for billions of years. As your breathing slows and deepens, imagine yourself floating in the peaceful space between worlds, held safely in the gravitational embrace that connects all things in this vast cosmic dance. The moon's story continues to unfold above us each night, writing new chapters in starlight across the dark canvas of space, while we rest secure in the knowledge that its faithful presence will greet us again with each new dawn. The moon's magnetic field remnants tell a story of planetary evolution that stretches back to the earliest days of our solar system. While the moon today lacks a global magnetic field like Earth's protective magnetosphere, sensitive instruments have detected patches of ancient magnetism preserved in certain lunar rocks. These magnetic fossils suggest that the moon once possessed a much stronger magnetic field, generated by a molten, convecting core that has since cooled and solidified. The strength of this ancient field may have rivaled Earth's own magnetic protection, creating a very different environment on the lunar surface billions of years ago. The gradual weakening and eventual disappearance of the moon's magnetic field had profound consequences for its evolution. Without magnetic protection, the solar wind began stripping away any atmosphere the moon might have retained from its formation or volcanic outgassing. This process transformed the moon from a world that might have supported a thin atmosphere into the airless body we see today. The timing of this magnetic field collapse may have determined whether the moon could have maintained surface water or other volatile compounds during its early history. Studying these magnetic remnants provides insights into the thermal evolution of planetary interiors. The moon's magnetic field likely persisted for several 100 million years after its formation, powered by heat from radioactive decay and the gradual cooling of the lunar core. As this internal heat engine wound down, the magnetic field weakened and eventually vanished, leaving only the fossilized magnetic signatures we can detect today embedded in ancient rocks. The moon's orbit around Earth is not perfectly circular, but follows an elliptical path that brings it closer and farther from our planet in a regular cycle. This orbital eccentricity means that the moon's apparent size in our sky changes slightly throughout each month, appearing largest when it reaches the closest point in its orbit, called perigee. During these closest approaches, the moon can appear up to 14% larger and 30% brighter than when it's at its most distant point, or apogee. These variations in lunar distance create corresponding changes in tidal strength on Earth. When the moon is closest to us, its gravitational pull is stronger, creating higher high tides and lower low tides than average. These extreme tides, combined with the alignment effects during new and full moons, can create what oceanographers call king tides, periods when coastal flooding becomes more likely even without storms or other weather-related factors. The elliptical nature of the moon's orbit also affects its apparent motion across the sky. When the moon is closer to Earth, it moves faster along its orbital path, while it moves more slowly when farther away. This variation in orbital speed, combined with the moon's synchronous rotation, creates a subtle rocking motion called libration that allows us to see slightly more than half of the lunar surface over time. Through libration, patient observers on Earth can eventually glimpse about 59% of the moon's total surface area. Lunar libration occurs in multiple forms, each revealing different hidden regions of our celestial neighbor. In addition to the rocking motion caused by orbital eccentricity, the moon also appears to nod up and down due to the slight tilt between its rotational axis and orbital plane. These combined motions create ever-changing perspectives of the lunar limb, occasionally bringing features normally hidden on the far side briefly into view from Earth. The moon's surface composition varies dramatically between different regions, reflecting the complex geological processes that have shaped it over billions of years. The bright highland areas, which dominate much of the visible lunar surface, consist primarily of anorthosite, a rock type rich in the mineral plagioclase feldspar. These highlands represent the original lunar crust that formed when the moon's surface was covered by a global ocean of molten rock early in its history. As this magma ocean cooled, lighter minerals floated to the surface while denser materials sank toward the interior. The dark Maria regions tell a different geological story. These areas were created much later when massive impacts cracked through the highland crust, allowing dense, iron-rich magma to well up from the lunar interior and flood the impact basins. The resulting basaltic lava flows created the smooth, dark plains we see today, which early astronomers mistakenly thought were actual seas. Each mare represents a chapter in lunar volcanic history, with some forming over 3 billion years ago, while others are relatively young at only 1 billion years old. Between the ancient highlands and the younger Maria lies a complex landscape of geological boundaries, where these different rock types meet and interact. These contact zones preserve evidence of the impacts that created the basins, the volcanic processes that filled them, and the subsequent bombardment that has modified both terrains. Future lunar exploration missions will likely focus on these boundary regions where multiple geological processes have left their marks in the lunar landscape. The chemical composition of lunar rocks reveals surprising connections to Earth's geology, while also highlighting fundamental differences between the two worlds. Lunar samples contain many of the same elements found in Earth rocks, but in different proportions that reflect the violent processes of the Moon's formation. The relative abundance of certain isotopes in lunar samples supports theories about the Moon's origin in a giant impact event, while also providing clues about the composition of the early Earth before this collision occurred. One of the most striking differences between lunar and terrestrial geology is the virtual absence of water-bearing minerals in moon rocks. While Earth's rocks commonly contain water locked within their crystalline structure, lunar samples are remarkably dry, suggesting that the Moon formed under conditions where water could not be retained. This difference has profound implications for understanding both worlds' early evolution and the processes that allowed Earth to become a water-rich planet capable of supporting life. Trace elements in lunar rocks tell stories of cosmic bombardment and volcanic activity that span the Moon's entire history. Rare metals like platinum and iridium, more common in asteroids than in planetary materials, appear in higher concentrations in certain lunar samples, marking periods when the Moon experienced intensive bombardment from space debris. These chemical signatures provide a record of cosmic events that affected the entire inner solar system during its chaotic early years. The Moon's gravitational influence on Earth extends beyond ocean tides to affect the solid planet itself, in ways both subtle and profound. Earth's rocky interior responds to lunar gravity much like the oceans do, creating solid Earth tides that cause the ground beneath our feet to rise and fall by several inches each day. These movements are too gradual and gentle for humans to perceive directly, but they're large enough to affect sensitive scientific instruments and must be accounted for in precise measurements of Earth's shape and gravitational field. The cyclical stress created by these solid Earth tides may influence geological processes in ways that scientists are still working to understand. Some researchers have proposed connections between tidal stresses and the timing of earthquakes, volcanic eruptions, and other geological events, though these relationships remain controversial and difficult to prove definitively. The idea that our celestial companion might influence the timing of dramatic geological events adds another layer to the complex relationship between Earth and Moon. Even Earth's atmosphere experiences tidal effects from the Moon's gravitational pull, creating subtle but measurable variations in air pressure that follow lunar cycles. These atmospheric tides are much smaller than ocean tides but can be detected by sensitive barometric instruments. The effects are most noticeable in the upper atmosphere, where the thin air responds more readily to gravitational influences than the dense air at Earth's surface. Lunar soil contains microscopic treasures that preserve records of solar system history spanning billions of years. Embedded within the fine regolith are tiny particles of solar wind, cosmic ray tracks, and even microscopic diamonds created during impact events. These nanoscale features turn each grain of lunar dust into a time capsule containing information about conditions in space throughout the moon's long history. The solar wind particles trapped in lunar soil provide a direct sample of the sun's output over geological time, allowing scientists to study how our star's activity has varied throughout its lifetime. This information helps us understand not only solar evolution, but also how changes in solar output might have affected Earth's climate and the development of life throughout our planet's history. The moon serves as a natural archive of solar activity that would be impossible to study any other way. Cosmic ray tracks preserved in lunar rocks offer insights into the high-energy particle environment of our local galaxy. These microscopic scars, created when energetic particles from deep space strike atomic nuclei in lunar minerals, accumulate over millions of years to create a record of galactic cosmic ray intensity. By studying rocks of different ages, scientists can trace how our solar system's journey through the galaxy has exposed it to varying levels of cosmic radiation. The lunar regolith also contains exotic materials created during the most violent impact events in solar system history. Glass beads formed during massive collisions preserve chemical signatures of both the impacting objects and the lunar rocks they struck, creating natural laboratories for studying impact processes that shaped all the terrestrial planets. Some of these impact glasses contain rare elements that provide direct samples of asteroids and comets that collided with the moon billions of years ago. Lunar volcanic activity created unique geological features that have no equivalent on Earth due to the moon's airless environment and lower gravity. Volcanic eruptions on the moon would have produced spectacular fire fountains that scattered molten droplets across vast distances, creating glass deposits that sparkle in reflected sunlight. Without atmospheric pressure to contain volcanic gases, these eruptions would have been dramatically different from terrestrial volcanism, creating landforms and rock types found nowhere else in the solar system. The timing and distribution of lunar volcanism reveal important clues about the moon's thermal evolution and internal structure. Most volcanic activity occurred between 3 and 4 billion years ago when the moon's interior was still hot enough to generate large volumes of molten rock. The concentration of volcanic features on the near side of the moon suggests that this hemisphere had a thinner crust or different thermal properties that allowed magma to reach the surface more easily. Some lunar volcanic deposits contain surprisingly high concentrations of water and other volatile compounds, challenging earlier assumptions about the moon's dry nature. These volcanic glasses may represent some of the most accessible sources of water on the lunar surface, potentially more valuable than polar ice deposits for future human missions, because they're located in areas with better solar illumination and easier access. The cessation of major volcanic activity on the moon provides insights into how small planetary bodies evolve thermally over time. Unlike Earth, which remains volcanically active due to its larger size and internal heat sources, the moon's smaller mass meant that it cooled more rapidly and could no longer sustain the internal temperatures needed for widespread volcanism. This thermal evolution pattern may be typical of many moons and small planets throughout the solar system. Seismic activity on the moon, while much weaker than earthquake activity on Earth, provides the most direct information available about the lunar interior. Moonquakes occur for several different reasons, including tidal stresses from Earth's gravity, thermal expansion and contraction of the lunar crust, and ongoing adjustment to the moon's gradual cooling and shrinkage. The patterns of seismic wave propagation through the lunar interior reveal a complex internal structure with distinct layers and possibly partially molten regions. The Apollo seismic network, which operated for several years after the last human mission to the moon, detected thousands of small moonquakes and provided the foundation for our current understanding of lunar internal structure. These seismic signals revealed that the moon has a small metallic core surrounded by a thick mantle and crust, but with proportions very different from Earth's internal structure. The moon's core represents a much smaller fraction of its total mass than Earth's core, supporting theories about the moon's formation through impact processes. Some moonquakes appear to originate from great depths within the lunar interior, suggesting that the moon may still retain pockets of partially molten material billions of years after its formation. These deep moonquakes follow monthly cycles that correlate with Earth's gravitational influence, indicating that tidal forces continue to stress the lunar interior in measurable ways. This ongoing seismic activity demonstrates that the moon remains a geologically active world, though at levels much reduced from its violent early history. The moon's seismic properties also affect how it responds to new impacts from meteorites and other cosmic debris. When large objects strike the lunar surface, the resulting shock waves can trigger moonquakes throughout the interior, creating seismic events that last much longer than typical earthquakes. This prolonged seismic ringing suggests that the lunar interior has different physical properties from Earth's interior, possibly including regions where rock behaves more like a rigid solid than the flowing plastic material found in Earth's mantle. Temperature variations across the lunar surface create complex thermal environments that change dramatically with the sun's position and the local topography. Equatorial regions experience the most extreme temperature swings, baking in direct sunlight for 2 weeks, before plunging into bitter cold for another 2 weeks. These temperature cycles stress lunar rocks and may contribute to the gradual breakdown of surface materials over geological time. Near the lunar poles, the temperature environment becomes more complex due to the interplay between topography and solar illumination. Some crater rims remain in perpetual sunlight, creating oases of warmth in an otherwise frigid landscape, while nearby crater floors lie in permanent shadow where temperatures never rise above the freezing point of shadowed regions serve most substances. These permanently as natural cold traps where volatile materials can accumulate and persist for billions of years. The thermal properties of different lunar materials create variations in how quickly surface temperatures change when sunlight arrives or departs. Areas covered by fine dust heat up and cool down more rapidly than regions where solid rock lies closer to the surface. These thermal differences can be observed from orbit using infrared instruments, providing a way to map the thickness and physical properties of the regolith layer across the entire lunar surface. Understanding lunar thermal environments is crucial for planning future missions and potential human settlements. The extreme temperature variations pose significant challenges for equipment design and habitat planning, while also offering opportunities for thermal energy storage and management systems. The stark temperature contrasts available on the lunar surface could potentially be harnessed to generate electrical power through thermoelectric devices that convert temperature differences into usable energy. The moon's rotation and orbital periods create lighting conditions that vary dramatically across its surface in ways that affect both scientific observations and future exploration plans. While Earth experiences relatively predictable day-night cycles, the lunar surface faces lighting conditions that can persist for weeks at a time. This creates opportunities for extended solar power generation in some regions, while presenting challenges for missions that must survive the long lunar night. The slowly changing angles of sunlight across the lunar surface create shadows that migrate across the landscape over periods of days and weeks. These moving shadows reveal topographical details that remain hidden under direct illumination, allowing orbital observers to map surface features with remarkable precision. The interplay of light and shadow across lunar terrain creates an ever-changing landscape of revelation and concealment that continues to yield new discoveries about surface features and geological processes. Some regions near the lunar poles experience unique lighting geometries where the sun remains low on the horizon for extended periods, creating persistent twilight conditions unlike anything experienced on Earth. These areas of perpetual low-angle illumination may offer advantages for future lunar settlements, providing consistent but gentle solar energy input while avoiding the extreme temperature swings experienced in equatorial regions. The moon's influence on Earth's climate extends beyond the obvious tidal effects to include subtle but potentially important impacts on atmospheric circulation patterns. The gravitational perturbations caused by the moon's orbital motion create small but measurable effects on Earth's rotation rate and axial orientation that may influence long-term climate patterns. While these effects are much smaller than those caused by solar variations and other climate drivers, they represent another way that our celestial companion continues to shape Earth's environmental evolution over geological timescales. As these lunar revelations continue to unfold in the quiet spaces of your mind, let them carry you deeper into the peaceful rhythms of rest. The moon's ancient light has illuminated countless nights throughout Earth's history, guiding migrations, inspiring dreams, and marking the passage of time with its reliable cycles. In its steady presence overhead, generations have found comfort and wonder, just as you might find solace in these gentle facts drifting through your consciousness like moonbeams through a window. The gravitational embrace that holds the moon in its eternal dance around Earth also holds you gently in this moment, connecting you to the same cosmic forces that have shaped worlds and guided the evolution of life across billions of years. As your thoughts begin to slow and soften like the fading light of evening, imagine yourself floating peacefully in the vast space between worlds, cradled by the same invisible forces that keep planets in their paths and stars in their courses. The moon continues its patient journey above, writing stories in starlight that will continue long after these words fade into the quiet darkness of sleep. The moon's gravitational field creates invisible corridors through space that spacecraft can navigate like celestial highways. These gravitational pathways, mapped by decades of orbital missions, reveal how the moon's uneven mass distribution creates regions where objects can travel with minimal energy expenditure. Future missions may use these natural routes to move efficiently between different lunar orbits. Much like sailors once followed ocean currents to reach distant shores with favorable winds. The discovery of these gravitational highways has revolutionized mission planning for lunar exploration. Spacecraft can now follow complex trajectories that would have seemed impossible to earlier generations of space navigators, using the moon's own gravity to guide them through intricate orbital maneuvers. These pathways connect different regions of lunar space in ways that make previously inaccessible areas suddenly reachable with existing technology. Some of these gravitational corridors remain stable for months or years at a time, while others shift and evolve as the moon's position relative to Earth changes throughout its orbit. Mission planners must carefully time their launches to take advantage of these temporary celestial highways when they offer the most efficient routes to their intended destinations. Lunar ice deposits near the poles contain more than just frozen water. Recent analysis suggests these ancient ice reservoirs also preserve other delivered to the moon by comets and asteroids over volatile compounds that were billions of years. Carbon dioxide, methane, and ammonia may all exist in these permanently shadowed regions, creating natural chemical libraries that preserve samples of materials from the outer solar system. These ice deposits represent time capsules from the early solar system, containing materials that have remained unchanged since they first arrived at the lunar poles eons ago. The extreme cold of the permanently shadowed regions has acted like a natural freezer, preventing these volatile compounds from sublimating back into space and preserving them for future study. The thickness of these ice layers varies dramatically across different polar regions, with some deposits extending several meters deep while others form only thin surface coatings. This variation suggests that ice accumulation has been an ongoing process throughout lunar history, with different areas experiencing different rates of delivery and preservation depending on local topographical and thermal conditions. Understanding the composition and distribution of these polar ice deposits is crucial for planning future human missions to the moon. Beyond providing water for drinking and life support, these deposits could supply the raw materials for rocket fuel production, allowing future lunar bases to become stepping stones for missions deeper into the solar system rather than dead-end destinations. The moon's surface contains natural glass formations that record moments of extreme violence frozen in time. When large meteorites strike the lunar surface, the intense heat and pressure of impact can instantly melt and vaporize rock, creating glass that cools and solidifies within seconds. These impact glasses preserve chemical signatures of both the striking object and the lunar material it encountered, creating natural laboratories for studying collision processes. Some impact glasses contain microscopic spheres of metal that were created when the heat of collision separated different elements and allowed them to condense into pure metallic droplets. These tiny metal spheres, smaller than the width of a human hair, represent some of the most extreme manufacturing processes in the solar system, where temperatures and pressures exceed anything humans can create in earthly laboratories. The distribution patterns of impact glasses across the lunar surface tell stories of cosmic violence that shape the entire inner solar system. Large impact events created glass deposits that extend for hundreds of kilometers from their source craters, marking moments when objects the size of mountains struck with energies equivalent to millions of nuclear weapons. Each glass formation represents a snapshot of conditions during impact events that lasted only minutes, but released more energy than all of human civilization has ever produced. These frozen moments of cosmic violence continue to yield insights into the processes that shaped not only the Moon, but all the rocky planets during the solar system's chaotic early years. Magnetic anomalies scattered across the lunar surface create invisible shields that deflect the solar wind in ways that continue to puzzle scientists. These localized magnetic fields, remnants of the Moon's ancient global magnetism, interact with charged particles from the Sun to create complex patterns of electromagnetic activity. Some of these magnetic regions appear to protect the underlying surface from space weathering, preserving rock compositions that would otherwise be altered by constant bombardment from solar wind particles. The interaction between these magnetic anomalies and the solar wind creates phenomena similar to Earth's auroras, though on a much smaller scale and invisible to the naked eye. Sensitive instruments can detect the ultraviolet emissions created when solar wind particles are deflected by lunar magnetic fields, revealing ongoing electromagnetic processes that make the Moon more dynamic than its static appearance suggests. These magnetic regions also influence the behavior of lunar dust, causing it to levitate and move in ways that differ from areas without magnetic protection. The electrostatic charging of dust particles interacts with local magnetic fields to create complex patterns of particle motion that may affect the design of future lunar equipment and habitats. Some magnetic anomalies appear to be growing stronger over time, while others seem to be weakening, suggesting that the Moon's magnetic environment continues to evolve even billions of years after the global magnetic field disappeared. This ongoing magnetic evolution represents another aspect of lunar geology that remains active and dynamic, despite the Moon's ancient and seemingly unchanging appearance. Subsurface structures beneath the lunar surface create gravitational signatures that reveal hidden geological features invisible from above. Dense regions buried deep within the lunar crust create subtle variations in gravitational pull that can be detected by sensitive instruments aboard orbiting spacecraft. These gravitational maps reveal ancient impact basins that have been completely buried by later geological processes, as well as dense intrusions of material that welled up from the lunar interior during volcanic episodes. The gravitational signatures of these buried structures provide insights into lunar geology that would be impossible to obtain through surface observations alone. Some buried features appear to represent impact events even larger than the visible basins on the lunar surface, suggesting that the Moon experienced bombardment so intense that they completely reshaped its internal structure multiple times throughout its early history. These hidden geological features also influence how seismic waves travel through the lunar interior, creating acoustic shadows and reflections that help scientists map the Moon's internal structure in 3 dimensions. The combination of gravitational and seismic data reveals a lunar interior that is far more complex and stratified than early models suggested. Future lunar missions may target these gravitationally anomalous regions for exploration, as they likely contain rock types and mineral compositions that differ significantly from surface materials. The gravitational signatures suggest that some of these buried features may contain samples of the deep lunar interior that were brought to shallower depths by impact events, providing accessible windows into the Moon's internal composition. The lunar surface experiences constant bombardment from microscopic particles that create effects both subtle and profound. Micrometeorites, most smaller than grains of sand, strike the lunar surface continuously at velocities of tens of kilometers per second. These tiny impacts gradually pulverize surface rocks into the fine dust that covers much of the moon, while also creating microscopic glass beads and welding dust particles together into complex aggregates. This continuous sandblasting process, called space weathering, gradually alters the optical properties of lunar surface materials, darkening them and changing their reflective characteristics over millions of years. Areas that have been exposed to space weathering for longer periods appear darker than freshly exposed materials, creating subtle color variations across the lunar surface that reveal the relative ages of different geological features. The cumulative effect of billions of years of micrometeorite bombardment has created a surface layer unlike anything found on Earth. This impact-generated regolith contains a mixture of glass, metal, and rock fragments that has been repeatedly impact-welded, broken apart, and re-welded into complex composite materials with unique physical and chemical properties. Understanding space weathering processes is crucial for interpreting observations of not only the moon but also asteroids and other airless bodies throughout the solar system. The moon serves as a natural laboratory for studying how prolonged exposure to the space environment affects rocky surfaces, providing insights that help scientists understand the evolution of countless other worlds. Tidal heating within the lunar interior may still generate small amounts of internal warmth billions of years after the moon's formation. As Earth's gravity flexes the lunar interior during each orbital cycle, the resulting friction converts mechanical energy into heat. While this tidal heating is much weaker than the geological forces that power Earth's interior, it may be sufficient to keep small pockets of the deep lunar interior slightly warmer than they would be from cooling alone. This residual internal heating may explain some of the ongoing seismic activity detected within the lunar interior, as well as the possible presence of partially molten regions revealed by gravitational mapping. The gradual release of this tidal energy over billions of years may have influenced the moon's geological evolution in ways that scientists are only beginning to understand. The distribution of tidal heating within the lunar interior varies with depth and location, creating complex thermal patterns that evolve over geological time. Areas of the lunar interior that experience the strongest tidal stresses may remain warm enough to support limited geological activity, while other regions cool to the ambient temperature of space. This ongoing tidal interaction between Earth and Moon also gradually transfers rotational energy from Earth to the lunar orbit, causing both the lengthening of Earth days and the Moon's continued retreat from our planet. The energy budget of this system connects the Moon's internal thermal state to Earth's rotation in ways that will continue to evolve over billions of years. Lunar soil mechanics present challenges that extend far beyond the simple absence of air and water. The regolith's behavior under the extreme temperature variations of the lunar environment creates conditions unlike any terrestrial material. During the long lunar night, the soil contracts and becomes more brittle, while the intense heat of lunar noon causes expansion and changes in grain-to-grain adhesion that affect how the material flows and compacts. The electrostatic properties of lunar dust create additional complexities for equipment design and human operations. Charged particles from the solar wind give lunar dust grains an electrical charge that causes them to cling to surfaces and resist normal cleaning methods. This electrostatic adhesion becomes stronger in areas where the dust has been disturbed by human or robotic activity, creating increasingly problematic conditions for long-duration missions. Understanding how lunar soil behaves under different loading conditions is essential for designing foundations for future lunar structures. The low-gravity environment means that soil-bearing capacity calculations developed for Earth applications must be completely reconsidered for lunar construction projects. The absence of moisture also eliminates many of the chemical processes that give terrestrial soils their engineering properties. Future lunar missions will need to develop new techniques for working with regolith that take into account its unique physical and chemical properties. From excavation and grading to concrete-like construction materials, every aspect of lunar soil engineering will require innovative approaches that have no terrestrial equivalent. The moon's far side serves as a natural radio quiet zone that could revolutionize astronomy and communications. Shielded from Earth's electromagnetic interference by the bulk of the lunar mass, the far side provides the most radio-quiet environment in the inner solar system. This natural protection from human-generated radio signals makes it an ideal location for sensitive radio telescopes that could detect faint signals from the early universe or search for communications from other civilizations. Radio telescopes on the lunar far side could observe frequencies that are completely blocked by Earth's atmosphere or overwhelmed by terrestrial radio interference. These observations could reveal new aspects of cosmic phenomena that remain invisible from Earth-based observatories, potentially revolutionizing our understanding of everything from solar system physics to the structure of the early universe. The stable, airless environment of the lunar far side also provides ideal conditions for other types of astronomical observations. Without atmospheric distortion or weather-related interruptions, optical telescopes on the moon could achieve unprecedented resolution and sensitivity. The moon's slow rotation means that astronomical targets remain visible for weeks at a time, allowing for extended observations that would be impossible from Earth. And so our gentle journey through the moon's countless mysteries draws to a close. We've wandered from its violent birth and cosmic collision to the quiet tidal forces that still shape our days, from ancient volcanic fire fountains to the pristine silence of its far side observatories. Each revelation has been a thread in the vast tapestry that connects our world to its faithful companion, a reminder that even in the darkness of space, nothing exists in isolation. As your thoughts drift now towards sleep, carried by the same gravitational currents that guide our celestial neighbor through its eternal orbit, remember that the moon continues its patient watch overhead. Its light has blessed countless generations before you and will illuminate countless more to come. In its steady presence, there is both mystery and comfort, both wonder and peace. Let these lunar secrets settle gently into your dreams, where they can continue their quiet work of connection and discovery. Sleep well, knowing that somewhere above, the moon keeps its ancient vigil, writing stories in starlight that will endure long after we have all become part of the cosmic dust from which worlds are born.